Welcome to this subsection on corrective measures and the section on neural machine translation with TensorFlow. We've just seen how an encoder-decoder model based on RNNs could be used in building a neural machine translation model. In order to come up with better results, we shall explore other models which are used in solving the problem of machine translation. Now, one of these is the attention mechanism, and also we have the transformers which are based solely on attention. Many different types of attention mechanisms exist, but in this section we shall discuss and apply the Bahdanau attention and the dot product attention, or more precisely the scaled dot product attention. Here we have the paper entitled Neural Machine Translation by Jointly Learning to Align and Translate by Dimitri Bahdanau, Kyung-Young Cho, and Yosho Benjo. Let's look at the abstract. Neural machine translation is a recently proposed approach to machine translation. So this is machine translation using neural networks basically. And that's what we saw with the encoder-decoder sequence-to-sequence models. Unlike the traditional statistical machine translation, the neural machine translation aims at building a single neural network that can be jointly tuned to maximize the translation performance. The models proposed recently for neural machine translation often belong to a family of encoder-decoders. An encoder sells sentence into a fixed length vector from which a decoder generates a translation. So that said, in this case where we have this encoder and this decoder, here we have our generated fixed length vector. So from this hidden and then the cell state, the hidden state and the cell state, we have this two generated fixed length vectors which are going to be fed into the decoder. So this is what they're referring to. It's true we have this dense layer which comes to modify this fixed length vector, but it's to be understood that basically this is the information that passes from the encoder to the decoder. Now in this paper, they conjecture that the use of a fixed length vector is a bottleneck in improving the performance of this basic encoder-decoder architecture, and propose to extend this by allowing a model to automatically, that's the soft search for parts of a source sentence that are relevant to predicting a target word without having to form these parts as a hard segment explicitly. With this new approach, we achieve a translation performance comparable to the existing state-of-the-art phrase-based system on the text of English to French translation. Furthermore, qualitative analysis reveals that the soft alignments found by the model agree well with our intuition. Now let's look at this from the slides right here. We see that suppose we are having a word or we're having a sentence, I love deep learning. We see that with the encoder-decoder model, we somehow have to come right to this end and collect this and then pass it on to the decoder for it to tell us that that means j'aime l'apprentissage approfondi, for example. Now, with the method they are trying to develop right here, we aren't leaving that huge task of understanding the input or the encoder information using only these output vectors. We are letting this decoder interact with each and every one or each and every part of the encoder. So the decoder will interact with I, will interact with love, will interact with deep learning, will interact with each and every other word to be able to come out with its own output. So we don't only depend on this. And it's also very clear that if we have a very long sentence, suppose we have a sentence made of an input, or suppose we have inputted say 1,000 word text, not just a sentence but now a text. So we have 1,000 word text that's inputted. We'll be counted on only these vectors to understand all those 1,000 words. Whereas with this method, given that the decoder actually interacts with each and every one or each and every part of the input, no matter how long our text is, we'll always obtain better results than just this encoder decoder kind of structure. Let's take a look at the background. From a probabilistic perspective, translation is equivalent to finding a target sentence Y that maximizes the conditional probability of Y given a source sentence X, that is argmax P of Y given X. In neural machine translation, we fit a parameterized model to maximize the conditional probability of sentence pairs using a parallel training corpus. So that's the input output. Once the conditional distribution is learned by a translation model given a source sentence, a corresponding translation can be generated by searching for the sentence that maximizes that conditional probability. So here we have works that go in line with this. And this neural machine translation approach typically consists of two components, the first of which encodes a source sentence and the second decodes. For instance, two recurrent neural networks were used by Cho et al., Sika et al. To encode a variable length source sentence into a fixed length vector and to decode the vector into a variable length target sentence. Despite being a quite new approach, neural machine translation has already shown promising results. Now, in this section of learning to align and translate, they propose a novel architecture for neural machine translation. The new architecture consists of a bidirectional RNN as an encoder. This can be modified into whatever encoder you want, and in practice we shall use the LSTM encoder simply. Now, and a decoder that emulates searching through a source sentence during the decoding. So instead of the decoder to rely on just that vector coming from the encoder, is going to go through the source sentence word by word before taking the decision of which word to output at a given position. Now, in a new model architecture, we define each conditional probability as given as such. Now, this probability of yi, of getting a particular word yi, depending on previous words and the input, is a function which depends on the previous word. That's if we add this, suppose we add this yi, so it depends on yi minus 1. It depends on the hidden state, the current hidden state, that's si, and it depends on this context vector ci. So this is very important to note right here. And this context vector is computed as a weighted sum of the annotations hi. Because here it is noted that unlike the existing encoder-decoder approach, here the probability is conditioned on a distinct context vector ci. So that's what we said already. And for each target word yi. Now the context vector ci depends on the sequence of annotations h1 up to ht. So it depends on the hidden states of in this case bidirectional RNN. But in the case where we have an LSTM, a GRU, is going to be something very similar to that. We're just going to use the hidden state. Now this already shows us how we are using all the input sequence in order to predict a given word. Like we will see from here, the probability of having a given word depends on all the input sequence, since ci is computed from using each and every part of the input sequence. Now, as we saw, in order to calculate ci, we've made use of alpha ij and hj. But then what is this alpha ij? Now this alpha ij, as we said here, is the weight of each annotation hj, and it's gotten using this softmax function. So to have alpha ij, like in this case to alpha t1, we have e to the power of e tj. Let's replace t by I, so we have e to the power of e ij divided by the sum of e to the power of e ik, where k goes from 1 to tx, or the sequence length. Now to obtain this alpha i's, we make use of this formula where we have eij equals the function a of si minus 1 hj. But then this is not just a formula, it's very representative of the attention process, where this A is an alignment model which scores how well the inputs around a position J and the output. Note, yeah, the inputs, and yeah, we have just one output. So we have this output at position I, and we have the inputs around a given position J. So if suppose we had this position J, the inputs around this, how well they perform, or how well these inputs match with a given output. And it's this score that is later on passed to form or to give us our context vector, which is used in finally predicting whether a given word is the best fit output or not. Now we parameterize the alignment model A as a feed-forward neural network, which is generally trained with all the other components of the proposed system. So this is very interesting because we don't have to separate this from the whole system. This just some weights which can be learned actually while learning the other weights in the or parameters in the whole system. Note that unlike in traditional machine translation, this alignment is not considered to be a latent variable. Instead, the alignment model directly computes a soft alignment which allows the gradient of the cost function to be backpropagated through. This gradient can be used to train the alignment model as well as the whole translation model jointly. So this is what we just said. We can understand the approach of taking a weighted sum of all the annotations as computing an expected annotation. So here we're explaining what the context vector calculation signifies. So as computing an expected annotation where the expectation is over possible alignments, let alpha ij be a probability that the target word yi is aligned to or translated from a source word xj. Then the ith context vector is the expected annotation over all the annotations with probabilities alpha ij. Now you could take our course on probability. If you don't get words like expected, then this probability and all of that, you could take our course on probabilities, so you could catch up with this. Nonetheless, you could continue without understanding each and every word that was said in this paragraph. Now the probability alpha ij or its associated energy eij, note that we obtained alpha ij by passing a softmax on the eij's, reflects the importance of the annotation hj with respect to the previous hidden state si minus 1 in deciding the next state si and generating yi. So the decoder decides parts of the source sentence to pay attention to. By letting the decoder have an attention mechanism, we relieve the encoder from the burden of having to encode all the information in the source sentence into a fixed length vector. With this new approach, the information can be spread throughout the sequence of annotations, which can be selectively retrieved by the decoder accordingly. Now, if you look back, we'll actually see that once we have this inputs, we're going to compute the eij's, that's the energies. From the energies, we have this weights alpha ij, which is the softmax of the energies, and then we have the context vector, which is obtained finally. While noting that the energy or the alpha ij's actually represent the attention to which or how similar a given output is with each and every of the input sequences, or with each and every word in the input sequence. So suppose we have an input sequence, I love deep learning, and then it happens that the position or the selected position output I falls at the level of M. So recall that I love deep learning in French stands for j'aime l'apprentissage approfondi. Now if we're at the point of M, or we're at the level where the word is M, then that function or this alignment model we define right here will be trained such that the value of eij will be the highest where we have in the word love. So since M and love have a great relationship, then the value of EIJ will be maximized whenever we fall at M. So if, for example, this is I love, so if we have this alpha T2 will have the highest values when we are concentrating on a given output M. And this now becomes very interesting, as we can know which of the inputs contributed the highest in selecting a given output. So as we can see, with the attention mechanism, we can now train over a longer range. So with the encoder decoder model, where training over a longer range, we have the issues of gradient vanishing and gradient explosion, because we are having very deep networks, and also with the fact that if we have a very long input sentence, then that context vector, or rather that vector which is going to be used by the decoder in outputting the words or the output words, is not going to be good enough to make the best decisions, because our input sentence is very long. Now with attention mechanism, that problem is solved. We also have less training time. As with attention mechanisms, we're dealing with less deeper models. We can now do parallel computation very easily. Now note that with RNNs, parallel computation is more difficult as compared to working with ConvNets or working with attention models. So now that we're working with attention models, it becomes very easy to do parallel computation. And when we say parallel computation, this means we can now do faster computation, especially on devices like GPUs, which make use of, or which make great use of parallelization in order to speed up calculations. As we said previously, no vanishing and gradient explosion. And then finally, transfer learning has become now more possible in NLP thanks to this attention model. We've looked at the Bahdanau paper and we've gotten a clear idea of how the attention mechanism works. Now let's take another example from database systems to understand better how this attention mechanisms work. So suppose we're having a database with keys and values, and then we have a query. So a query is just like a demand. So supposing we're having a very large database of keys, where we could take keys like some IDs and then values like be somebody's name. So suppose we're having this large database of IDs and names, or a student database, for example, and then you have this query of students who are of age, or rather student whose names start with A. So we're gonna come here for each ID, or we get the values. Now if the value starts with A, then this is selected. So suppose we are having this kind of database where we have a query, or where we can input queries, and then we have the keys and values, which when a key is selected we can obtain as value. We could actually compare this with the attention mechanism, where the SI-1 that we have right here is seen as the query, and then the HJs are seen as the keys, and then the HJs which are used to obtain the context is seen as the values. Now a more formal way of rewriting the attention mechanism is that we have attention, which takes in queries, takes in keys, or it takes in a query, we'll say a query, takes in keys, takes in values, and that's the output is the sum for I of the similarity between the queries and the keys times the values. And if we come back here, we have this A acting as the similarity function between the queries and the keys, and then when we have this, we pass through the softmax, which is now this. So we could take this as the EIJ. So this now is like the similarity between the query and the keys, and then this is the values. And we can have different similarity functions. We have the dot product similarity function, we have the scale dot product similarity function, we have the general dot product similarity function, and we have the additive similarity function. The Bahdanau is the additive similarity function, while the dot product or the Luang type is the scaled dot product similarity function, which is one of the most widely used. Now let's take a more detailed view of the Bahdanau attention mechanism, which was presented in the paper. Suppose we have this input right here, or this input LSTM layer we have right here, and then an output LSTM layer, which is going to produce the outputs that we have here, and then this one we take in the inputs, and then we shall go for every point in the output sequence length. So we have this position, we look at the hidden state 0, that's the initial hidden state. This is the query which we are going to pass into our attention mechanism. So right here we have that query which comes in. We have the keys. Now the keys here are actually gotten, as you could see from this. We have the keys. So these keys are gotten from the outputs of the LSTM layers, or LSTM layer, since it's a stack of many LSTM layers. And then from here, a similarity is going to be computed between this input query and then the keys, which are all these different outputs, because we have just this one query and then we have this different keys. Now we pass this in, we have this query which comes here. This is it right here. We see how this position of this output position actually is going to be compared with each and every input position right here. Now the dimensions have been put so that it could be understood very clearly. So right here we have dimension, the batch size, we have 1, since it's just one value, and then we have H2, that's the number of hidden units we have here. So that's basically what we have for our query. That's the kind of tensor we have which passes in to our attention. And then we have here again, we have the batch size 1 and then H. Now you could, for simplicity, you could have H1 equals H2, so that doesn't cause any problem. So for that, we just have this B1H1, which is going to be repeated everywhere. So here is going to be B1H1 up to this one, which is going to be B1H1 to this B1H1, this B1H1. Now if all of this is combined, we're going to have BLH1, since the sequence length is L. For now we have this, so we have B1H1 which passes into the attention model. We have the query which gets in. We have B1H2 and then B1H1. Now for the next we have again B1H2 and then B1H1. But note how this particular query is going to be computed, or the similarity between this query is going to be computed between the query, that the similarity is going to be computed between the query and each and every key, that is each and every value of the input sequence, and that's very important. So we have this, it passes through a dense layer with activation function tanh. We have the H2 which tends to U, because the dense layer has U outputs, so we leave from H2 to U, and then here the same from H1 to U. And then once we have this new tensor of dimension B1U, this other one B1U, this is actually two tensors. Recall that this is additive similarity function, since we're dealing with the Bahdanau attention mechanism. So we have this and this. Now they're gonna be concatenated, and then we're gonna pass it again through a dense layer. So once we concatenate this and then pass it through a dense layer which has only one output, we're gonna have B11 to the batch size 1, which is this, and then after this dense layer which has only one output, obviously we'll leave from U to 1. So note that this is concatenated before dense, and then we have this. So once this is done, we have B11 right here. So this is now for just this comparison, and then we move to the next, right up to the end. So we're gonna go through all the sequence length. So this is gonna be for this, let's suppose this is 1, 2, right up to L. And these values, or this tensor we have right here with this dimension B11, happens to be the energies EIJ we had seen previously. So after computing the similarity between Si minus 1, in this case we're computing the similarity between the H0, let's just say S0, because H0 is going to be confused with this 1. So we're computing the similarity between S0 and all the different hidden states we have here, or all the different outputs in the case of the slides. So basically that's what we're doing, and that's how we obtain these energies. Now after we obtain these energies, note that if we combine them all, we're going to be having a tensor of dimension batch size, sequence length L, and 1. So it's just going to be all this different energies for each and every part of the sequence length. Now after this, we pass this through a softmax layer. So we are passing this BL1 through a softmax layer. If this is passed through a softmax layer, we now have the weights alpha ij. So after the softmax layer, we have the weights alpha ij, and the weights have the same dimensions as the energy. So we end up with still this batch size, the sequence length 1. And now if we look at this again more critically, if we take off the batch size, we're left with L1. Now L1 simply tells us here that we could take off this 1 and we just have L. So we're having this L dimension vector, which tells us how similar each of the keys is to the query which has been inputted right here. And this is very important because it shows us how much attention we have to pay on a particular key or a particular output from here when having a given word. So if, for example, right here we have the word G, because let's say je, because French is je, and then yeah, right here we have I, and that in this vector the very first of the values has the highest. It tells us clearly that this je and then the I are actually highly correlated, or there is much similarity between the two. Now let's move on. After this softmax, we now go into calculating the context vector. To calculate the context vector, we're simply multiplying this softmax output with the values. Now in this case, the values is going to be the same as the keys. So basically that's what you see here. We have this branch from the keys, takes and gets in, next branch takes from there, next branch from here. So we're simply taking these keys having the same dimensions as the values, or rather we're taking these values having the same value and dimensions as the keys. So that's basically what we have here. So we pass in this, and then we record that the have the dimension B1H1. So for each of them we have B1H1 times B11. Now we're saying B11, supposing that we have not considered all this as one, we're considering them as separate entities in this output softmax. So if we have B11 from here, that's each of this is broken as we've broken it, as you can see this broken lines here. So if we break it also this way, we have B11, and then L of them gives BL1. So we have B11 times B1H1 plus B11 times B1H1, and so on and so forth. And then if we have to combine all of that, it gives us BLH1. So this is the dimension of the output after the context vector. And from here we could see that this process can be repeated as we go through the whole output sequence. So for this first one, we have this attention, and then for the next, as you could see, so for the next we pass through this. Now instead we have this attention, the next we have this attention, and so on and so forth. Then once we have this value right here, we pass through a reduce sum operation to give us this tensor with dimension batch size H1. So this L dimension is crushed using the reduce sum operation, and then that's what's passed as an input into this. So we know the output, we pass this as now input, and then we train the model fully. Now, as we said, from here to obtain this, or rather to continue the attention process, we take this value too, pass it through this. We have this other block, attention block, the same as we had seen here. We have also this attention block which goes right up to the last value or last cell state or last hidden state in our output. We pass through this. This is the query right here. We have the keys as we have seen from here, the keys, the values passed, and then we have reduce sum, and then we have this. So it's something that's very repetitive, and we repeat this. That's this block. Each block is repeated L prime number of times, whereas in each block this is repeated L number of times. But now it should be noted that to do computation actually programmatically, we are going to just combine all of this as one dense layer. Recall that in TensorFlow, if we're having a 2D or two-dimensional input, a dense layer knows that and takes that into consideration. In the case where we have a 3D input, like supposing that instead of having the B1H1, that's instead of having each of the keys getting in as separate entities right here, which is actually the case, and that's why we're doing this, because we want you to understand exactly what happens. But now let's suppose that we are passing in all the keys at once. So we have B. Now in this case we took L to be 21 to make it look more practical. So we have in a B 21 H1. So the sequence length we have here is 21. Now the query is B1 H2 as we had seen, or B1 H1. There's no problem with that. And then we pass it through a dense layer. We pass this through a dense layer. Here, the dense layer was going to output B21U. So it's going to represent all this dense layer, this one, right up to this. So it's going to be like a mother dense layer, which represents all this 21 or L dense layers. So practically, this is how it's going to look like. We have this dense layer, we have this, and then we're going to concatenate that, then pass it through a dense layer again, and then we have the same output we had right here. From this, now it remains the same. So that's basically it. And then also here, instead of doing the multiplication and then addition, we could always just do that for all L at once. So that's why we see here that to obtain the context vector, we have BL1 and then BLH1. Recall that the BLH1 is actually coming from the fact that the values now are now taken as 1, as BLH1 instead of B1H1 separately for all the sequence length. So this is now BLH1, this is BL1 from right from here, BL1 from the output of the softmax. So the BL1 now multiply with the BLH1, it gives us BLH1. Now we shall build the Bahdanau attention model using TensorFlow. So right here we could create something here. We have this where we get the query and then the keys. The values equals the keys as we had seen earlier. Then to obtain the energy, that's the EIJs we had seen in the paper, we have this computation right here. So this is actually, and this happens to be that additive similarity function which we had seen earlier. So this is the addition of this function which takes in the query, this is a function which takes in the keys, it's added up, and then we have the output, which is the energy or the similarity of a query and the different keys. And as we had seen in the slides right here, we have to pass this through a dense layer and this other one through another dense layer. Now we had also seen here that we could collect all the keys and then pass them through one dense layer, and then collect that query and pass it through the dense layer too. And that's basically what we do right here. We declare this dense layer WCure, that's the weights of the query, the weights of the keys, and then this weights, this combinatory weights right here. The weight of cure has it's a dense layer which outputs or with units number of outputs. This is actually the U we had seen in the slide, so we could have this U right here. Now let's get back to units, and that's fine. And then for this other dense layer, it has output just 1, as we had seen in the slides. So right here we have the dense on the query, and then this other dense layer on the keys. Then we go through the tanh function, and then finally through the W dense, that's this dense layer with 1 output. And with this we obtain the energy. Now while doing this, let's actually create a Bahdanau attention object and test all of this, so we could see how the shapes are modified as we go through. So we have Bahdanau attention, we have the query, we have the keys, we can now collect the outputs in this. But for now, let's not get to this. Let's have it like that. So we have this query with shape batch size. The batch size is 2. We have this 1 because we're selecting one of the queries. We have now the number of hidden units, and then same for here, where this is the sequence length. Now we could go ahead with that. So with this, we could run this, and then but before running that, let's print out the shape of the energy. So let's say energy shape, and we have energy that shape. So we'll run this, and that's fine. So now we have the 2, that's the batch size, the sequence length, and then 1. So that's basically the energy we obtain, and this tells us how similar each of the keys are with that particular query. Now let's turn this to a batch size of 1. So let's take this batch size of 1, and then let's take off the shape. Let's take this off, we'll run this, and that's fine. So now this tells us that this is the similarity between this. Could run it again, you could see that this tells us that this is the similarity between this query and each of the keys. Now for the first key, we have this, we have 0, 0, and all of that. But now when training, supposing we have inputs I love deep learning, for example, then if this is the first, so this is I, this is love, this is deep learning. Now at this position where we have this love, we should have the highest energy when we're dealing with a query at the position where we have the French word M. So when we select that query at the position where we have the French word M, normally after training, the energies should be restructured in such a way that this should have the highest value. So that's it for that, and then we'll move on to the next. We have now the softmax. We pass through the softmax. We see we select the first axis, because right here we have, let's print out the shape, print out that shape, take this off. Okay, so right here we have batch size, we have sequence length, and then we have 1, and the softmax is computed on this first axis, called we have the 0th axis, the first axis, and the second axis. So we're computing the softmax on this axis. That's why we select the first axis. Then after computing the softmax, we should have the same shape. So if we print out, let's say, attention weights, that shape, we should have the same as previously. So that's fine. Now once this is done, we now get into the context vector. So here we're actually doing a pointwise multiplication. So with the attention weights that we had previously, that's this one, this is the shape of our attention weights, and then the values obviously have the shape of the keys. So we have this. We're now multiplying this with this, and obviously that should give us a shape, or a tensor with shape, batch size, sequence length, and 32. So we could print this out. We have context vector that shape. Run that. We see that we have just that. We have the batch size, the sequence length, 32. That's because we have done a pointwise multiplication of the values, which in this case the keys of the values and the attention weights. So that's just fine. So that's how we obtain our context vector. Now once we have this, we pass it through a reduced sum where this sequence length dimension is crushed. That's why again we select the axis 1. We crush out this dimension. So from this, let's print this out. Print out context vector shape, run that. See, we have just that dimension is crushed. And once we have this dimension, we can now pass it as an input into our decoder. But note that what gets here is not just this byte size or this tensor of dimension byte size hidden unit number. It's actually byte size 1 and then hidden unit number. So that's why we have to expand the dimensions and include another dimension in between the byte size and then the hidden number. So that's what we do right here. We expand dimensions. We leave from this into 132. So we output that. That's what gets to the decoder. And then we also have the attention weights. Now the use of the attention weights we have, right, that's what we got after the softmax, is actually for us to visualize and understand which parts of the inputs are most related to the query. So with this, we'll be able to see that very clearly. And that's one of the great advantages of the attention mechanism. So with that, we leave from this, and now the output we got is this one right here, which can now get into the decoder. And then we have the attention weights. So that's it for the Bahdanau attention. Now note that TensorFlow comes already with a model which permits us get this without having to rewrite the code like this. Now what's left for us to do is to construct this encoder, construct the decoder, and then link them up via the attention mechanism. Now what's left for us to do is to build the encoder. So right here we could have this encoder, and then we have the embedding, and then the LSTM layer. Note that this LSTM outputs the sequences and the states, but we could take off this, so we could render this false. We don't take that into consideration. We're just taking only the outputs, and then obviously we don't have this, so we have that. So we could run this and then test this actually. So let's do this. We have this. Now suppose we have this input into our encoder. We'll define our encoder vocab size by the vocab input size, which later on gets into the embedding. And then after we have the embedding output, which we've defined right here, the embedding dim is 8. And then we have the number of hidden units, which we've defined to be 32, to match what we had right here. So this is going to generate the keys and the values. So that's why we try to match it with what we had previously. Now once we have this, we have the input into our encoder, which is this tensor of dimension byte size sequence length, and this is the kind of input our TensorFlow.datasets gives us. So what we have from here is something like this. So that's why we're already ready. So this encoder is ready to receive that kind of input with this. So once we have this, now we pass it through the encoder, through the embedding, through the LSTM, and then we have the output. So let's run this. That comes out clean. We have this output dimension 2 1032. That's the byte size. Now we could actually let's define the byte size right here. So let's say we have the byte. No, we defined that already. So let's just put it to be byte size. So we have byte size. We run this. You see, that gets the byte size we had defined previously. So now this is ready to get into the attention. But before that, let's define the decoder model. For the decoder, we shall go through the whole output sequence. And for each of these outputs, that's for this one, for example, we'll take this hidden state and pass it into the attention block, and then take the keys and the values from the inputs and pass 2 through the attention block. So this is going to be one attention block. Then we shall move to the next output. We take the hidden state, pass it into this next attention block, take those inputs, these keys and values, pass it into this, and so on and so forth. So we're going to have sequence length or output sequence length, number of attention blocks right here. So that's what we're going to do in the decoder model. And as you can see from here, we go through this. we have the attention, which collects the hidden state that we define from this. So we have that hidden state we get from the outputs, which we pass in here. We have X, which is actually the keys and the values which we get also, or which we shall call. And then after this, we have the context vector and the attention weights. Recall the attention weights could be used in visualizing how the inputs are related with the outputs. Now, once we have this, we go through an LSTM layer, which in this first output happens to be this one. So we go through this LSTM layer to have the output now. And then we shall repeat this with this other LSTM layer right up to the end. And so that's how we pass in the context vector into this LSTM layer. So we have many LSTM layers. That's why we have the teeth LSTM layer, and we've defined the LSTM layers such that we have a list of LSTM layers which go through for the range that's for the sequence length, and then we define each one. So for this particular one, let's say at 0, we have LSTM 0. So we pass through this LSTM layer, we get the outputs, we get a hidden state, we get the C. This actually is supposed to be C. We have that, but we wouldn't use this, so we could do that. So once we have this, we have now that hidden state which we will need it in the next attention layer or attention block. Recall that once we have this output, as you could see, we use this and it's going to be used in the next attention block. So that's why right here we collect this output and the hidden, we pass the hidden into, or we modify the hidden so that it could be passed into the attention block. That's why we add another dimension. We have now the outputs, which are, or with the outputs, this output list which we define here, which collects each and every output. So basically what we're doing is we're putting the outputs into this. Now the hidden has changed. We now have the hidden of the next value in the sequence, and is what's going to be passed into the next attention block, and we'll repeat this all throughout the sequence length. Once we have this, we now have the outputs from here. Once we have these outputs, we concatenate them, and then we pass through a dense layer so that this matches with the vocabulary size, and then we could output that. So from this, let's run this now. So run this. We have the decoder, which is equals to decoder that. We have the vocab output size. We have the embedding dimension. We have the number of units. We have also the sequence length. So that's it. And then we could call this. So we have decoder. We call the decoder. We pass in the encoder outputs. So we have the encoder outputs, which we had from here actually, which is going to be passed into the decoder. So we pass in this X, this is what we call X right here, the keys and the values. And then initially the hidden state is just 0. So we have TF the zeros, 1, and then the number of units. So we could run this. Now units is not defined. It's actually the hidden units which we had defined previously. Have this, run it again. This not defined. Hidden units. Encoder outputs not defined. We hadn't run this. That's actually output. So let's have this. Okay, so right now we have our expected output with dimension by size, the sequence length, and then the vocabulary size. Now if we combine everything we've just seen, we can have this embedding dim 100, sequence length 10, the inputs. Now we just have one input. Now we don't have like the encoder decoder model where we were implementing the teacher forcing where we had 2 inputs. Now we just have one input, but you could always include, or you could always implement attention with a teacher forcing too. So for this implementation, we are not using teacher forcing. Now with the encoder is basically what we've seen. We have the encoder, we have the encoder output, we pass it into the decoder. We have the encoder output which gets into the decoder. We have this which we define. We have the decoder which we've defined already. We define the model, and we can get the model summary. We run this. This is what we get, the input and then the outputs. So right here we could have this. We could also increase the embedding dimensions. So 1000. We have this outputs. We can now go ahead to train. So Basically this is what we have that, we have this, and then let's compile this and run this. We see that we have an error because we're not even using the same data set, so we have to modify our data set. So let's get back from the beginning. We had this, we don't have this again, so let's take this off right here. That's fine. So we could run this. Let's start from here. We have this, run this, we run this, we run this, run this, run this. Now we just have one input and one output. This is not more useful. Take this off, run this. This one not more useful, take it off. This is XY, so we have XY now, run it. Now we also have XY, but right here we have Y, so we'll run this again. Here we could take this off, so we don't need this. Run this. Right here we have the squeeze, and then we could take this off. This one right here, let's take this off. This is off. So we have the input and then the output. Run this. See, we have an error because of the Z, so let's take this off. Run this again. Now yeah, we don't have key anymore, so run this. That's fine. We have I and J, so that's good. Now we go to shuffling and then creating the training and validation. We have this, run it, take this, run it. Okay, so we've prepared our data set. Then we could come back to this point. So let's come back to this point. We'll run this, compile our model and run it again. Now after training for a while, we have these results which are quite poor. Our model is diverging. We could actually include the from logits right here. So from logits equals true. Stop that kernel, run again. We now see that our model actually converges. So with this, we could increase the number of epochs and then run this again without reduce the learning rate. Stop this, run it again. And then after this, we shall include the blue score and also the validation data set. Validation data equals validation data set. Now we obtain these results after training over several epochs. We could stop this and then include the blue score. Now after going through a few epochs, we can see the blue score, we can see the validation loss, and then the validation blue score. Let's just add this. So you could add this at this level, so you take off the message which comes up every time. As you can see, our blue score is increasing while our loss decreasing. Now let's go to testing. We have this, I will try. Now this is useless, we don't need this again. Pre-output not needed again. This, we only need one input. For the get output, we only take in just the input. So we have this, we have this, we have that, and everything is fine. So let's run this now. We have this, run this, N2 is not defined. Let's take this off, run this again. Okay, so that's the output we get, and then we'll run this. So we see that with this one now, we just one pass, no need for any teacher forcing, and we have the correct results. We could try some other stuff, like for example, ask him, run this, demand Louis. So that's quite good, and we could continue training. We could also increase the number of data points we're working with, basically increasing our data set. We could also increase the embedding dimensions right here so that we could have a larger model. We could increase the number of hidden units and all that. So that's how we build this using attention mechanism.